Hey everyone, my name is Stephen Hyde. I'm a senior physics student here at Alma College, and I want to talk to you today about something that I've been working on for a little over a year and a half now. So, last year, near around the end, or rather the middle of the first semester, I started working on a liquid-fueled ethanol and oxygen rocket engine. Now, at first, there were some major issues with the engine, but I did eventually manage to sort them out. Now, after posting the videos on YouTube, I was absolutely blown away by the amount of views and engagement I got on those first videos. I think the very first video has something like 28,000 views right now, and my most viewed video, the one that has just a compilation of several engine tests, has something like 75,000 views right now, which is absolutely mind blowing. And I'm just, I'm at a loss for words on just how amazing that is to be recognized for that and have so many people watch what I've done. But along with those views, I got a lot of people asking me questions about my rocket engine. I originally tried starting to answer them in text by replying to comments, replying to emails that I got, but eventually I realized that a lot of people were asking sort of the same questions. So I figured that it would probably be a really good idea to put all of that into a video and post that on my channel to sort of try to answer all of the questions that people were asking and maybe answer some questions that people hadn't decided to ask yet. So what this video is going to be a sort of a deep dive into the design process of my rocket engine, how I decided on what I did and didn't want the engine to do, and how that affected the design of that engine, how I decided on the fuels, materials, the shapes and overall dimensions of the engine, and everything about that. And then I'm going to go into how I actually made the engine. So how I machined all the parts, how I put everything together, got all the hoses and plumbing fitted up, and then I'm going to talk about the actual process of firing it. Hopefully, with that, I'm going to add some video of me actually doing all the things that I'm talking about, so machining parts and whatnot. Um, Although with that, you have to keep in mind that when I first made the engine, I wasn't expecting a whole lot of um, sort of fanfare around this. So I didn't record anything, and I just sort of just filmed the test footage, and that was that. So I'm gonna have to go back and re-record a lot of stuff. So I'm gonna have to remake some of the parts and record myself doing that. And with that, there are some parts that are a little bit more expensive than others. So the material for the combustion chamber is copper. Copper's pretty expensive, and for someone like me who has an income of no income, I'm gonna have to settle for some cheaper materials. But with that in mind, I'm still gonna be doing the same machining techniques, the same dimensions, everything like that is gonna be the same. It's just gonna look a little different. So keep that in mind as we go. Hopefully that'll answer all your questions. If I don't get to any of the questions that you have, or if the video brings up any more questions that you didn't have already, then please leave some questions down below and I will try to answer them in the comments. If I get a lot of questions or if I screwed up on something or if there were things that I left out, I may make a follow-up video for that, but we'll see how that works out. Anyway, let's go. Now, to start off, the goal of this project was never to make a rocket. It's to make a rocket engine. Now, that's a very big, important difference because a rocket does a whole lot of more things than a rocket engine does. Rocket needs to fly, it needs to go up and go down, ideally with some sort of parachutes that doesn't plaster itself on the ground when it falls. It needs to be relatively stable so it doesn't careen off in various different directions and into someone's house and kill them. It needs to be reliable enough so that it doesn't explode on the launch pad or shortly after launch. Now, a rocket engine doesn't need to do any of these things, really. It just needs to generate thrust, burn fuel, and ideally not explode. Although that, it happens, you know. So once I dispense with the idea of making a rocket, that makes my life a whole lot easier because instead of having to worry about weight ratios, thrust to weight ratios, the mass and size of components, how they'll integrate into the rocket, all I have to worry about is making the rocket engine safe and reliable, and so that it actually does what I needed to do without putting myself or anyone else in danger. Now, what this means in terms of the engine itself is that I don't need to worry about certain things that I normally would have to if I were designing an engine for an actual rocket. So first off, I can overbuild certain components, such as the combustion chamber, so that if anything were to go wrong, like a hard start, it's not going to fail catastrophically. It's not going to explode and send shards of shrapnel everywhere into people like me. I don't like having shrapnel shot at me at high speed, so that's a good thing. I can also not worry about the thrust to weight ratio. I can make it very low, less than 1, so that if anything were to go wrong with the test stand, it will just fall over instead of flying off somewhere where I couldn't find it and it could potentially get horribly damaged. Lastly, I don't have to worry about how close things need to fit together in terms of the plumbing. So I can have the oxygen tank and the fuel tank very separated. So that if anything were to go wrong in the oxygen tank or vice versa, they're not going to be able to mix very well and explode in a horrible giant fireball. Instead, it's probably just going to go and fizzle out, which actually did happen with the oxygen hose when things did go wrong. So I'm able to keep things very safe and under control, even when things don't go exactly as planned. Another limiting factor would be the available tools that I have. So at my college, there's a very small machine shop. There's only maybe 2 lathes, 2 mills, one of which is, I'm not sure how old it is, but it's seen at least 1 world war. So all of the fancy stuff like regenerative cooling channels or bell nozzles or injectors like coaxial swirl or anything like that, I can't do that because it's just not realistic with the tools available to me. So it also has to be really simple. At the same time, I also don't want to let that simplicity become a liability. So I need to make it very simple, but also very reliable and very safe. Speaking of safety, let's talk about the fuels. So to start out with, I need something that's relatively easy to get my hands on and relatively safe, something that I can store for long periods of time when I'm, going back and forth between classes, when I have exams to prep for, because I can't just be focused on this. I also had to be focused on, my regular schoolwork. So things like cryogenic propellants, which need very low temperatures to be stored at, specialized containers, which are very volatile, like liquid oxygen will oxidize pretty much anything that it comes in contact with. So it's pretty dangerous. And to top it all off, all of that stuff is very expensive. So I can't have any cryogenic propellants. Next up, hypergolics. Obviously no. No person in their right mind would let an undergraduate student store any sort of hypergolic propellant anywhere on campus. So that's out of the picture already. Also, I'm pretty sure I'd be breaking some kind of law if I were using a hypergolic rocket engine on on or near my college campus, which is where I'm based and doing all my testing. So that really leaves me with just the very bare basics. So for fuel, I have 3 options. One is gasoline. You can get that at any gas station. Kerosene, you can get that at some gas stations and other hardware stores, industrial suppliers. And then ethanol, which is pretty easily available from most industrial suppliers. So gasoline, I don't like that because it's pretty volatile and I don't want to deal with the added danger of it just combusting, of having fumes filling up the room, and then a spark happens and then I'm dead. Second, kerosene, I don't really like that because the stuff that I can easily get my hands on typically has too many impurities in it for it to be reliable, and I don't want it to gum up my engine or anything like that. So it really leaves me with just ethanol as my best option. So ethanol is pretty good. You can get it from most industrial suppliers as denatured ethanol. So that I got from McMaster Carr was 99% purity denatured ethanol. So that's 99% ethyl alcohol with 1% being made up of additive stuff like methyl alcohol and other nasty tasting stuff so that people don't drink it. And that works pretty well. It's the lowest performing of the 3 rocket fuels, but it's the easiest to get my hands on. I know it has very high purity, and I know it's reliable. And also I know that I can leave it just in a storage shed somewhere for long periods of time without it decomposing and exploding or anything like that. So now we have to talk about the oxidizer. So I've already ruled out a lot of options by saying that I can't use any hypergolic stuff. So no red or white fuming nitric acid, nothing like that, which also complicates the ignition process, but I'll get to that later. And I can't use any cryogenics, so obviously no liquid oxygen. Now, what does that leave me with? Well, as it turns out, the machine shop at my college also has a little welding station that pretty much never gets used. And next to it is there is a big acetylene tank and an oxygen tank. So I yoinked it. And oxygen, gaseous oxygen, tends to work pretty well as an oxidizer. It's not quite as good as liquid oxygen because obviously it's less dense and it doesn't mix quite as well with the same energy that liquid oxygen can. In addition, a lot of literature discussing gas on liquid injectors usually discusses it in terms of either pintle injectors or coaxial and or swirl injectors, which for the machine tools that are available to me and the machining experience that I have is just not realistic to expect to be able to reliably and consistently machine to the tight tolerances required to get good performances out of those injectors. So there was some learning as I went, but overall I think that gaseous oxygen as my oxidizer was probably the best choice that I could have made given all the limitations that I had. Now that we have our fuel mixture, gaseous oxygen and liquid ethanol, I'm going to talk briefly about the feed system that I'm going to use. I'll get back into it more detail later, but for now I'm just going to go over the basics. So what I decided to go with is what's called a pressure feed system. What that is you have your fuel tank, you fill it up mostly with your liquid fuel, and then the top you attach to a pressurized tank of inert gas. That tank fills the rest of that space with a high pressure gas to whatever pressure you want it at, and then when you open the fuel valve, that gas expands and pushes out the fuel into your engine. The main limiting factor for that is the pressure regulators that I can use in order to pressurize my fuel tank. Now, looking at the pressure regulators that were available to me in the machine shop, I had ones that could go up to around 250 psi. Based on that, and also knowing that the pressure drop across the injector should be roughly 20% of the chamber pressure, I decided to give myself a little bit more room and go with a nice round 200 psi. What that does is it keeps me well within the tolerances for the pressure regulator so I don't break anything, but it also gives me a relatively high chamber pressure for the size of rocket engine I'm using, so I can get some good combustion, good performance out of it as well. Now that we've talked about our fuel and our chamber pressure, let's talk about the actual combustion chamber itself. So what I decided to do is I went with the simplest design I could possibly go with, which was a heatsink type combustion chamber. What that is it doesn't use any sort of cooling methods like regenerative cooling, film cooling, anything like that. It's just a big hunk of metal that takes a long time to heat up, and in that time I'm able to get enough data that I'm fine with that. So I went with copper for the material of this combustion chamber because it has very good thermal properties. It's able to distribute the heat that it absorbs very evenly around its entire volume, and it's able to radiate that out pretty quickly. So despite having a relatively low melting point, it's able to withstand those temperatures for a surprisingly long amount of time. What that also means is that with the thick walls of the combustion chamber that's required by this heatsink design, it's also very, very strong. If you look at equations for pressure vessels, you'll see that wall thickness is very important. And when you have your wall thickness, I think this one was like 1.5 inches thick. At 200 psi, that thing's never bursting. Now that we've established some of these design parameters for our engine, let's talk about the dimensions of the combustion chamber. So there are a few key sections we need to consider when we're doing this. Starting at the top of the engine, we have the combustion chamber. This is where the propellant is mixed and burned. It needs to be large enough for the fuel to have enough time to burn completely before it enters the nozzle. But we also don't want it to be too large, or else it'll be very difficult to manufacture and pretty costly and expensive to do that. The nozzle is the next section below the combustion chamber, and that's what's used to direct the hot combustion gases in the combustion chamber and generate thrust. I'm going to break this up into 3 sections: the converging section, the throat, and the diverging section. These 3 sections together take advantage of the principles of fluid dynamics to accelerate the high pressure gases in the combustion chamber in order to produce thrust. And here's how. So inside the combustion chamber, the gases are very high pressure, but they aren't moving very fast. Now, using Bernoulli's principle, we know that to accelerate a fluid, in this case the combustion gases, traveling at subsonic speeds, we need to make the section it's flowing through narrower. That's why the converging section of the nozzle narrows as it goes towards the throat. However, this only works up to a point, and at the narrowest point of the nozzle, this is also known as the throat, the gas is going to be moving at the speed of sound. And making the nozzle any narrower won't accelerate the gas any further, and it'll only restrict the flow. Now this is where it gets interesting, because when your fluid is moving at speeds equal to or greater than the speed of sound, the relation we saw with Bernoulli's principle flips, and we can accelerate the gas further by widening the nozzle. This is called the diverging section of the nozzle, and this is what accelerates the combustion gases from the speed of sound to speeds in excess of 2 or 3,000 meters per second. The necessary volume of the combustion chamber can be determined roughly by comparing the ratio of the combustion chamber volume, including the converging section of the nozzle, to the area of the throat. This value is known as L star, and you can look up L star tables based on your fuel and oxidizer in many textbooks and online sources. For gaseous oxygen and ethanol, we should be shooting for an L star roughly of somewhere between 200 and 250 centimeters, or 79 and 100 inches. That is our minimum. We can go above that and we'll be fine. But if we go below that, we'll have some losses in efficiency because the burning propellant will not have enough time to have fully combusted and expanded into a gas by the time it leaves the nozzle. And so we'll have a much higher pressure drop than we expect across our injector. We'll have lower pressure inside the combustion chamber and lower thrust from our engine. I actually had this problem last year when I was working on the first version of my rocket engine. Now, I was shooting for a chamber pressure of roughly 150 psi, but because my combustion chamber volume, my L star was too low, I could never get above 130 psi, and that was with a pressure drop of, instead of 50 psi that I was aiming for, I was actually having a pressure drop of over 100 psi across my injector. For my design, I wanted to make my dimensions as simple as possible. So the throat is made with a 1/4-inch drill that I just drilled through the center. And then the combustion chamber itself is going to be drilled out with a 1-inch drill bit. The angle of the converging section is going to be made by the angle on the drill bit, so 118 degrees from the center line. The overall length of the copper rod that I'll make my combustion chamber out of is going to be 6 inches long, with 0.2 inches on the top being used to connect the injector assembly, and the 1/2 inch on the bottom being for the nozzle section. Originally, I made this from 2 separate pieces, since I miscalculated the dimensions as I mentioned previously, and I had to just make another small little chamber extension and resize the nozzle on that to make everything work better. But for the sake of this video, I'm going to be using a single piece, so just keep that in mind. These dimensions end up giving us an L star of roughly just over 100 inches, which should ensure that the fuel is completely combusted by the time it leaves the nozzle. Normally, this nozzle section should have an expansion ratio such that the pressure of the gas exiting the nozzle is roughly equal to the surrounding atmosphere. We can see in this diagram that for our chamber pressure of 200 psi, we're going to want an area expansion ratio of about 2.74 to 1 from the exit area to the throat area. Now, I didn't do that. Instead, I decided to make my nozzle slightly underexpanded to make the machining process a little easier for me. And as an added side effect, we have some really cool shock diamonds in the videos that we see, which is always nice. I'm going to have my nozzle exit be just under 1/2 an inch wide, and it's going to taper in towards the throat at an angle of 14 degrees from the vertical. To actually machine the combustion chamber, I'm going to put it on the lathe. First, I start with a very long 1/2 inch drill bit that I'm going to drill to the exact length that I want my 1-inch drill bit to go. So that just makes it easier to cut with the 1-inch drill bit instead of having to drill straight through solid metal. Now that I've measured out and made sure that that 1/2 inch drill bit has gone exactly as far as I need it to be, then I come in with the 1-inch drill and I slowly work my way down until I have the exact depth that I want for my combustion chamber. Now that that's finished with, there's one more thing I want to do before I flip it around to work on the nozzle, and that's to make a 2-inch wide recess about 0.2 inches deep on the top of the combustion chamber. Now this is where the injector plate and the injector manifold, where the fuel and oxygen come into the injector, are going to be sitting. So I carefully take a boring bar and I just scrape out exactly that size, and then I fit it, and once it's fitted, I can move on to the nozzle. Now that all that's done on the top, we can flip it over and start working on the nozzle. So to start out, we're going to drill a 1/4 inch hole, which is going to be our throat section. And then we're going to come in and we're going to start cutting away our nozzle section by setting our compound rest on the lathe at a 14-degree angle, and then just slowly walking in until we've got the right exit size that we want. Now, in this footage, I've actually made a little screw up. Instead of coming in at a 14-degree angle, I'm coming in at a 24-degree angle. So just keep that in mind. The very last thing we're going to do on the lathe is cut the bottom 1/2 inch from 3 inches down to 2 inches in diameter. What this does is it lets it sit inside the retaining flange on the bottom so that nothing shifts around while you're putting it together or while you're operating it. I don't have any footage of this, so you're just going to have to look at a picture of it and watch me talk. So sorry about that. Speaking of things that I don't have footage of, I also want to have added a method of measuring the pressure. So what I'm going to do is I'm going to drill a very small hole. What I did was I chose a 0.1 inch drill, and I drilled a very small hole into the side of the combustion chamber. There I added a 1/8 inch NPT tapped hole for a compression fitting to fit into. Connected to this compression fitting is going to be a foot-long 1/8 inch copper tube, which connects to another pressure fitting where my sensor is attached. What this does is it gives it just enough so that the pressure can propagate up that tube, but it's not so big that it'll like blast out or have so much heating from the combustion gases that it'll melt anything. So this works really well to measure the pressure. I've been able to do it very easily and measure very precisely the pressure in the combustion chamber without any major drawbacks to the combustion performance. So now that we have the combustion chamber completed, I'm going to move on to what is arguably the most important part of the engine, the injector. This is what controls the flow of oxygen and fuel into the engine and ensures that the two are properly mixed together so that they will ignite reliably and burn efficiently. Without it, the engine simply wouldn't function. When dealing with propellant mixtures of gases and liquids, typically what you want to do is either use a coaxial, swirl, or pintle injector. Very simply, these all involve coaxial tubes with varying degrees of complexity that, unfortunately, with the small injector area that I need for the engine, I just don't have the machining skill or precision to manufacture with such tight tolerances. So instead, what I'm going to use is an impinging type injector. Now, these aren't optimal for gas-on-liquid injectors because when the gaseous oxidizer is injected, it will spread out very quickly instead of spraying in a nice stream like a liquid would. So when this happens, you won't get the optimal mixing characteristics that you would for a liquid-on-liquid injector that is impinging. But that's okay, because honestly, in this small scale, the losses in efficiency from that aren't too bad, especially for triplet injectors. Doublet injectors, it's a little bit worse. You can find several different injector designs in the link in the description to a Google Drive folder where I keep most of the information for my rocket engine on. But for this particular design that I'm going to be talking about in this video, it's an unlike impinging pair, but the fuel is oriented in a like impinging pair. So there are two fuel holes and one oxidizer hole, and the fuel holes impinge on each other and spray out in a fan, and then that fan impinges on the gaseous oxidizer spray. Hopefully this should provide pretty decent mixing characteristics, but I don't know yet because I haven't tested it. So we'll find out together later on in this video if that's actually the case. Injector hole sizing can be determined using this equation from Leroy Kozicki's How to Design, Build, and Test Small Liquid-Fueled Rocket Engines, and based on design guidelines from this textbook, Modern Engineering for Design of Liquid Propellant Rocket Engines, we want a pressure drop across the injector of at least 20% of the total chamber pressure. Otherwise, there'd be risk of combustion instability and even a possibility of the flame traveling back up the fuel and oxygen lines if anything were to go wrong. This means that our pressure drop across our injector should be roughly 40 psi. And I've decided to increase that for the oxygen port to 50 psi just in case anything weird happens. And after plugging these parameters into the equation, I found that my two fuel holes should be 0.028 inches in diameter, and the oxygen hole should be 0.109 inches in diameter. To drill them, I used a number 70 drill bit and a 7/64 drill bit, respectively. The injector plates are made from 2-inch diameter, 1/8 inch copper discs I bought off Etsy. Apparently these discs are originally meant for jewelry or something, but they do the job. The way they're punched out, though, leaves them slightly convex on one side, which is good, since that allows a good solid seal against the combustion chamber without the use of an O-ring, thus reducing complexity. However, this means that the other side is concave, and we need to flatten that out in order to be able to properly drill the holes without having the drill bits walk all over the place. Now that we've flattened everything out on that side, we're now ready to drill the injector holes. As for the drilling itself, there's not much else I can say than it's a very slow and careful process, and a lot of drill bits get broken along the way. Now that we've covered the injector plate, we're going to take another step up and talk about what gets the fuel and oxygen to that injector plate, which is the injector manifold. For the oxygen, we have a simple 1/4 inch hole drilled all the way through the center, which at the top is threaded for a 9/16 UNF insert, which corresponds to the threads on my oxygen hose. The fuel system is a little more complicated. Since we don't have room to put the fuel hole on the top, we need to go in through the side. I start by drilling the 1/4 inch hole that will connect to the downcomer, and then I use a 1/2 inch drill to widen the outside of that hole so I can thread it for the 9/16 inch UNF hose fitting. Before we drill the hole that would bring the fuel to the injector side of the manifold, we have one problem to address first, which is that for this project, I want to have it be applicable to multiple different types of injectors. So I need to potentially design for the fact that the fuel holes may not be in the same place, that you could have one on one side and then the other on another side, or at right angles to each other angles, what have you. So for this purpose, we need to be able to distribute the fuel all the way around in a ring. So I put a 1/4 inch wide channel just 20 thousandths of an inch deep around in a ring so that the fuel can be distributed evenly. Since I'm doing it on the lathe, I'm also going to put on some O-ring grooves to keep the oxygen and fuel separate, as well as to prevent any unwanted upstream pressure drops. The last parts of the engine are the 2 retaining flanges that go on either end of the engine and hold the whole thing together. I started with a pair of 2 4-inch diameter 1/2 inch steel discs. I decided to use 6 3/8 inch bolts to hold the whole engine together, though this caused some issues with the length since I ended up having to buy new longer bolts, and then it still wasn't long enough when I extended the engine. This was when I made that combustion chamber extension that I talked about earlier. The moral of the story there is just use threaded rods and not bolts. Just saves you hassle. Anyway, for the top flange, I drill a 1-inch hole in the center so I can access the oxygen port, and then 6 3/8 inch holes in a circular pattern around the outside. These are 1 3/4 inches from the center so that I can avoid interfering with the combustion chamber. The bottom flange is very similar, with 6 holes for the connecting bolts. However, the hole in the center is going to be 2 inches in diameter, so the combustion chamber can fit nice and snug in that little recess. That's it for the engine itself. Here you can see me putting it all together. I tighten the bolts in opposing pairs in order to make sure the pressure is applied evenly. The plumbing for the engine is relatively simple, and since this engine isn't actually meant to fly, I can do a lot of things that I wouldn't normally be able to do, which generally make my life easier. First, I can use flexible hoses instead of more rigid pipe work, which is just more easy to deal with, allows for greater flexibility and whatnot. Second, I can also use larger or heavier and thicker fuel tanks, which means that I don't run into the issue of having it accidentally be too thin, too weak, overpressured, or anything like that, and have it burst or fail in some way. I can just have something that's way overbuilt for the purposes that I need it for, and so I don't have to worry about any safety issues regarding that. I can also use large oxygen and pressurization tanks, which normally wouldn't fit on a rocket because they're way too big. Now, this provides me with a lot of freedom to just test as much as I want without having to worry about getting it refilled, repressurized, anything like that. The oxygen supply line starts at the oxygen supply tank. This connects to a pressure regulator set at 250 psi and then goes via a welding gas hose to a ball valve. The ball valve is then connected to the engine via a braided steel hose. It's braided steel because originally I had used welding hoses. This, by the way, was marketed as a oxygen gas hose specifically. But that had an alarming tendency to become hybrid rocket fuel in the presence of gaseous oxygen. The fuel line is a little more complicated. It starts at the argon supply tank, which then connects to a pressure regulator set at 240 psi. This pressurizes the fuel tank, which is a 300 milliliter Swagelok. I'm not sure how to pronounce it. I'll put it up on screen. Double-ended sample cylinder. The pressurized argon is connected to the top of the tank with a welding gas hose, and a hydraulic fluid hose connects to the bottom of the tank, which then goes to a ball valve and then to the engine. Here's what this setup looks like in practice. I've been testing the engine on the loading dock of my college's science building, and you'll notice that the engine is in this sunken area right here. Now, there's also a large slab placed over the top of it, and that's to contain any rapid unplanned disassembly incidents, which actually works remarkably well.
The valve operating station is here, safely behind this nice brick pillar. And you can see these hoses leading to the oxygen and argon tanks over here, safely far enough away so that if anything were to go wrong, they won't detonate, which so far hasn't happened. Here's a video of the actual testing procedure.
The engine test stand, where the engine sits during testing, is made up of 3 steel angle bars welded together. The engine sits in the center and butts up against the force sensor, which is mounted on the back here. The wonderful thing about this design is that it takes advantage of the fact that the engine has a thrust-to-weight ratio that is less than 1. So even though it's very simple, there's no actual danger of the engine flying away if something were to go wrong. That's pretty much all there is to talk about for the test stand itself, so I'm now going to move on to the igniter system. Now, I've gone through 3 ignition systems so far. The first and crudest was just a burning rag soaked in kerosene that I shoved up the nozzle. This worked once, but it was very unreliable and it tended to go out when it was inserted into the combustion chamber due to a lack of oxygen. So I very quickly replaced it with a spark gap ignition system. The spark ignition system consists of a 9-volt battery hooked up to a transformer, which has 2 wires running off of it. The ends of those 2 wires are stripped, and then the wires are twisted together so that the stripped ends are about a 1/4 inch apart. I then take this and I insert it up the nozzle and secure it with electrical tape. When the circuit is closed, this will create a spark across that gap between the 2 wires, and that spark is very hot, and that is able to ignite the oxygen and fuel mixture. This works really well, and it's very reliable. However, I eventually ran into a problem that is when the arc jumps instead to the combustion chamber, the very conductive copper combustion chamber, rather than the other wire, it somehow, for some reason, creates a very strong electromagnetic pulse, which knocks out the force sensor. It just turns off. Now, I've tried a lot of things. I've tried separating the test stand from the engine itself so that no physical contact is made and so no current can travel through that to the force sensor. That didn't work. I tried insulating the wires with special shielding covers. That didn't work. I tried making a little Faraday cage for the Arduino for the force sensor's Arduino. That didn't work. So eventually, I just had to decide that enough was enough, and I moved on to something else. That something else is a pyrotechnic igniter, or more simply, a sparkler. This is really simple, and it's very reliable. The great thing about sparklers is that they have their own oxidizer built into that mixture that burns, which means that it's not going to have any problem with oxygen starvation that the burning rag did. Another bonus is it's very cheap. Every 4th of July, you can get hundreds and hundreds in cardboard boxes, and they last a good long while. So I had some in my shed out back behind my house. Just grabbed them, and they work really well. For data acquisition, I have 3 main things that I use. 2 of which work with Arduinos, so I'll try to get the code somehow put in like a Google Drive or something. I don't know, and then in the description of this video, I'll do something with that. The force sensor is just a load cell that's mounted to the test stand that the engine butts up against it. When the engine fires, it pushes against that and it gathers force data. That's connected to an Arduino Uno, which then feeds data into my laptop. Connected to another Arduino is the pressure sensor, which connects to the engine via that small port we added in the combustion chamber earlier in the video. To record footage, I use my iPhone 12's camera, which has a slow motion feature, which allows me to record footage at 240 frames per second. It's really nice, it's very useful. This high frame rate allows me to gather tons of information about what's happening at any given moment during the test. If something goes wrong, I can usually see at least hints and clues as to what happened. And if something goes well, I can analyze the footage and see what's actually happening, get an idea of how the engine startup process is going and whatnot. And the high frame rate just lets me see things that I normally otherwise would miss. for gathering data on the engine and making sure that all, or at least most, of the systems that function as they should and don't fail, there are a few main tests that I run. 3 of these involve the injector assembly. The first test is to determine the discharge coefficient of the injector plate. And to do this, what I do is I run water at high pressure through the injector plate and into a bucket. I can then weigh the bucket to determine how much water over a given time has gone into the injector. The way I determine the time is by taking a high-speed video of the fuel valve. I've marked off at what point the valve opens so that water can pass through it. So I just time how long it takes me to open it. When it passes that first one, that's the first mark. And then when I close it, when it passes that mark the second time, that's the second. Take the time between the 2 intervals, and that's your change in time. Now, after I do this a bunch of times, I can then average out the data and find what flow rates it has at given pressure drops. That helps me determine the discharge coefficient, and that helps me then determine what the performance is of the rocket engine itself when it's firing. The second test is the cold flow injector test. This involves running water at higher pressure as well as gas through the injector assembly to simulate the fuel and oxygen flowing through the engine while it's running. This helps me identify any problems with sealing, both in the hoses and the fittings, like if anything is leaking, if any water is where it shouldn't be, as well as to identify any sealing issues between the fuel and the oxygen itself. Because you don't want any premixing, you don't want any pressure drops prior to the fuel and oxygen getting to the injector face, because then if there's not enough pressure, if there's not enough back pressure in the fuel line, in the oxygen line, then if you have a hard start, that can then propagate up the fuel and oxygen line and have catastrophic results. Now, this kind of test can give you a rough idea of the mixing performance as well by visually assessing the atomization of the water as it is sprayed from the injector. The third is the injector hot fire test. This is pretty much the same thing as the cold flow test, only the actual fuel and oxygen is used and it's run through the injector rather than water and inert gas. What I do is I have a blowtorch sitting right in front of the injector face so that when the oxygen and fuel is sprayed out, it's ignited. I can better assess the mixing characteristics of the fuel and oxygen from the injector by looking at how well it ignites, where it ignites, what happens when it's actually burned, and it also just looks really cool. I like it a lot. Last is the hot fire test itself. This is only done after all the other tests have been conducted and no major faults or problems have been found during those tests. The injector we'll be testing here is the new injector I made earlier during this video. Let's watch. All right, ready? In 3, 2, 1. Now, that was pretty cool, right? So there are a few things I want to talk about in regards to this test. First is this is the first test using the sparkler ignition system, which worked really well. Now, unlike in previous tests using the spark gap igniter system, there was no delay between the fuel valve opening and ignition occurring. Next, this is actually kind of surprising for me, is the performance of the injector itself. Now, compared to the more conventional, unlike the impinging doublet design, it had at best pretty much the same performance, and at worst, slightly underperformed. Now, this is despite having smaller fuel holes and a spray pattern that I assumed would provide slightly better mixing performance. The smaller fuel holes, as suggested by some of my viewers, was tried because it was thought that smaller fuel holes would mean a smaller stream that atomized more easily. We don't know if that's the case, but evidently it didn't make that much of a difference. Visually, it's very hard to make out. The exhaust plume is very washed out by the ambient light. That's because, it was very snowy when I recorded this video, and so the ambient light reflected off the snow, sort of washed out, and made it very hard to see the exhaust plume. However, if we look really closely, we can just about make out the exhaust plume, and we can see that there appears to be some asymmetry, with the top of the exhaust plume being brighter and more visible than the bottom. This could possibly be caused by some non-uniform distribution of the fuel in the combustion chamber, as well as some improper mixing. I don't know for certain if that's the case because I can't see inside of the combustion chamber itself. That's a project that I'm going to be working on later, but for now, we just don't know why that is. Overlaying this image onto a previous test with a regular unlike impinging injector seems to show that the general shape of the exhaust plume is pretty much the same, which roughly correlates to the data that I get collected from my force and pressure sensors. So overall, we can conclude that this injector design, though more complicated and more difficult to machine due to the size of the holes used for the fuel injection and the compound angles at which the fuel holes are angled, it doesn't offer any real advantage over the more simple and conventional unlike impinging doublet design. There you have it, how I made my rocket engine. Now I will add that if you're watching this video with the hopes of making your own engine, there's a few things that you should keep in mind on top of all of this. Now, the first is that if you're going to be putting it in a rocket especially, it's going to have to be much lighter and much more powerful than my own rocket. So that means a lot of things, but mostly it'll have to have either a higher flow rate, higher chamber pressure, or both, as well as having much thinner chamber walls to contain all of that. What that means is that there's a lot of ways that this can go wrong very badly and very quickly for you. So be very careful about that. You know, when you're testing, do all of that with remotely operated valves and in places where nothing can be damaged, nothing can be destroyed, and no one's life or safety is put at risk. I would also highly recommend you do further reading on the subject. The primary sources that I used for this video are on screen now. They're all linked in the description down below. Anyway, that's all I have for this video. Please, if you have any questions, anything that I didn't cover, anything you want more detailed answers on, leave those in the comments down below and I'll try to get to them as best I can. If I get enough of those questions, I might make a follow-up Q&A video or something like that. And speaking of videos, since I'll be graduating in May, my rocket engine project sadly will be coming to an end relatively quickly, at least by the end of the year. But I still have a few more videos planned for the next couple months on the topic, and even after I graduate, I'll still probably have enough stuff to go over to tide me over for a couple more videos after that. So look forward to those, and in the meantime, thank you so much for watching. Bye!